I'll try and make this. But most of you, I don't know, at least some of you know a lot about this already. But I guess I should still include an introduction and stuff. So first I'll just review Chern-Simons vector bosons and bosonization, then we'll just test that functions. Then more, that I hope to spend more time on just some open questions which I'm thinking about, which may be slightly speculative, but they're a bit more related to like quantum space-time than this one. Okay. And it's based on several references. So most recently, I did this with a student he's from IIT Bombay, he recently graduated. And later on here I'll mention stuff from archive. So I'm sorry for So how much motivation about this do you want? Like, because many people already know this well, but I guess
give some motivation for those of us who don't look at that very actively.
Okay, so, I mean, yeah, I'll give. So the basic motivation is as follows. Okay, in general, constructing conformal field theories is difficult and requires supersymmetry, but the simple observation made by Shahs and Prakash was that in three dimensions.
I really like that.
By everyone.
It does that.
Whoever, I don't know whose idea it was, but the simple observation was that it's very easy to define conformal field theories in three dimensions thanks to the existence of Chern-Simons. Okay, and the reason, the way to do it is very simple because first, Chern-Simons action is, the coupling constant is based on k, which is an integer just because the action has to be single valued. So k cannot run. And so Chern-Simons series are automatically conformal. And then if we combine to say a fermion, fermions in three dimensions have mass dimension 1. So you can't write down any. If you just have fermions coupled to Chern-Simons case field, you can't write down any other interactions aside from the mass term. So the theory is automatically conformal. And if you consider A to be a UN gauge field where n is large, then you can work in the Hooft limit where n over k lambda is sort of fixed. So you have although k is discrete, you effectively have a line of conformal fixed points. Okay, but you can study a tweak coupling, and then you can see if something interesting happens with from coupling. Okay, so it's easy to generate CFTs in three dimensions using Chern-Simons. You can also just try to construct a CFT with bosonic fields. There you do have marginal operators like the lambda to the sixth, but perturbative analysis show that you can, for a given value of lambda, you can tune those to a fixed point. Okay, so even even if you had other fields, you would still get the CFT. It's just perhaps a bit harder to study. Okay, so the question is, since we have these CFTs with parameters that you can continuously deform, you can look for interesting strong weak dualities, which typically previously we believed to be just associated with supersymmetric CFTs, but they also might have turned out. We also discovered some interesting ones in non-supersymmetric CFTs. Okay, so the bosonization duality is a particular example of a non-supersymmetric strong weak duality, which I'll describe. So, are there any questions or concerns? So in principle, so let's. Okay, so the idea is if the duality is, consider a UNF KF Chern-Simons, that's fundamental fermions coupled to UNF Chern-Simons. And we can also consider, and on the other side of the duality we have so these are fundamental fermions.
This is the gauge group you're writing, UNF, or just
right? This is the gauge group.
Fundamental fermion, or how many fundamental fermions?
At present, we have one fundamental. We can later on ask about what happens when you have more fundamental fermions, which is more interesting. So one fundamental fermion, yeah, that's right. And we can write our theory with one fundamental boson. Okay, and ask is there a duality between them? Of course, there clearly, may not be a duality because, to get a duality, we have to consider not fundamental bosons, but also critical fundamental bosons, and so it turns out that there's a duality between these two, which takes the form KF. So the following two cities are equivalent, the critical fundamental bosons coupled to UNP and UNF fermions are equivalent with the following change of parameters. So in one description we have KF, in the bosonic description that's minus KB, and in NF is related to Well, I read this duality in terms of N and K, but it's only been tested in large N limit. And in particular, we do expect at least some shifts of 1/2 for consistency.
One could probably write down a precise conjecture of exactly what it should be and finite.
Right, so yeah, I can write that. Yeah, we can write that conjecture with plus or minus 1/2. I'm not 100% sure whether it would hold if I.
And couldn't you consider the bosonic theory for KB less than NP? As just as a field theory, is it not sensible?
Not in. Okay, so it depends how do we define the coupling. So if we define it in the dimensional reduction regularization, then you can't consider it for K less than NP. But if you consider it in terms of K Yang-Mills, then there's like a shift in it. So yeah, so it turns out it'll be not unitary with K less than NP if you define it using dimensional.
And, a way of saying that's invariant to the regulator is that if you ask what is the level of the Weissubin-Witten theory induced at the boundary of this theory, it's not kappa but kappa plus ink.
Right, so really kappa plus n is what I should write as k.
K.
But
Yeah.
in all the calculations we use this scheme. So
Just to point out that the regime that Sandeep was interested in would be like a negative k.
Which is just a parity.
No, okay, that would be negative 1.
Okay.
Good. And let me ask one more thing. The critical boson theory is what? What is it?
Yeah, so you take the usual bosonic theory and we deform it. So the usual bosonic theory is Chern-Simons coupled to bosons with lambda 6 term. You add this following term. Lambda 4 is dimensional, but you can take this double trace term. You take lambda 4 to infinity. Okay, so that without the Chern-Simons field, this is the predictable OM vector model in the absence of a Chern-Simons interaction. If you're familiar.
Right, okay. So you take the 5-4 theory and Wilson Fisher.
Which in the large n vector limit is relatively accessible.
That corresponds to taking the bare coupling to in some coordinate.
You know, in the way we do it, we just take lambda 4.
While holding the mass fixed.
We keep
physical mass.
Yeah, so we will just keep it 0.
So dimensional regularization, you just take it.
Right, otherwise you take it in a coordinate.
And then what about the 5-6 coupling?
So when you do this critical theory, the 5-6 coupling really isn't there anymore.
Yeah, you think of this as renormalizable quantum field theory. Oh, yeah, it doesn't matter, sorry. Yeah, this value goes away.
Right, because in the critical theory, in the non-critical theory, there's a 5-6.
Where is it going? It's marginal, no? It's 9 dimensional.
You see, in the critical theory, phi square picks up dimension 2. So in the critical theory, 5 to the 6 has dimension 6. So it's highly irregular. And you see that from when you actually take this limit, all physical answers become independent of phi 6.
Right. So this is one way of looking at it. Another way of looking at it is you can consider non-critical bosons coupled to critical fermions. Okay, so I can also describe that theory. So the critical fermionic theory, we just add a field sigma. You integrate over sigma, which is like the diffuse rounded transform, and then the new scalar operator in your theory is this sigma and not psi or psi. Sigma has mass dimension 1, so matches with the bosonic scalar operator. And
I see. So this is the 9th dimension.
This 9th dimension is the same as the actual dimension. Okay, and then here if you can have like a sigma cubed coupling which matches this, which corresponds to the bosonic
Phi 6.
phi 6. Yeah, we'll come to these. So this is the duality, and this is the map between duality. If we work in terms of lambda, it's lambda f equals write it in terms of the lambdas as okay, so the question is how do you test the duality, or how is it discovered? So the simple way of testing it is to calculate gauge invariant correlation functions on both sides and see if they match. Okay, so the unique. Okay, so in each theory, there's a unique single trace operator for given spin and scaling dimension. Okay, so in the fermionic theory, that would be, which I'll write, and that would be, so say this guy, and similarly in the bosonic theory, we have an operator which in the non-critical theory is phi squared. In the critical theory, it's closely related to phi squared. So to compare, the duality, we first have to find the relative normalization between these two operators. The two definitions, we calculate 2-point functions of each and set them equal to determine the relative normalization between the two operators, and then after that you have predictions for then all the 3-point functions and so on and so forth. Okay,
so sorry, what do you say here? So you have the
right, so we have so on each side we have a tower of gauge invariant operators.
Sure.
Okay, they're each labeled by their spin and scaling dimension. So the claim is that both operators are equal up to overall normalization,
and
which may depend on the coupling constants and other things. So to determine that normalization, we just compare the 2-point function.
and what is JB0? So it has to have dimension 2.
Right. So what JB0 is actually is. Okay, so it's given, it's in the critical. So if we were in the non-critical theory, it's just type dagger. Right, dagger. Then here we multiply it. We take a lambda f factors of lambda f to make the lambda for in the critical thing to give a dimension. This has,
So the ninth dimension of this operator is 1.
I guess it's lambda
is 2.
4.
And then you multiply with lambda 4, which goes to infinity, isn't it?
Right. So this. Well, this is the bosonic scalar, but when you calculate correlation functions, you get.
It's playing the role of the cutoff. You know, if an operator has 9 dimensions.
Oh,
It's just a cutoff.
Yeah.
Okay. All right.
So it's.
Fine, I got you. So in terms of the bare fields, it looks like phi dagger phi with this kind of.
Yeah, in terms of the bare.
Okay. All right.
Okay, so then we can calculate these, the 2-point functions of each. And in momentum space. And here, using this, we
The calculation is done with q plus minus equal to 0.
well, at this, it doesn't matter. As I say, because there's only one form.
But
You do the calculation always with q plus minus 0, but
you know
but
the
conformal invariance dictates the form uniquely. So we can calculate them both, to all orders in lambda f, the two-point functions, and if the two theories are dual, then these two different values just dictate the relative normalization of the operators.
Yes.
So, I mean, what you do, in effect, you have some showing a Dyson-like thing which you solve, huh? That's what you do.
How do we to calculate?
You sum the
Okay, so I mean, yeah, we sum the planar. Now, so I'll come to the calculation
This
in
is
a
not something
in a
that
minute.
was done in that first paper.
Yeah, it's not it's done, but it could have. I mean, yeah. So I'll say how we calculate these in a minute.
Okay.
In a minute, but yeah, so the claim that there's a duality means that you have to map these all. How do you extract predictions from the duality for calculations in both days? So first you calculate 2-point functions of these in each separate description. So if we're claiming these two operators are equal, then that this determines the relative normalization of the two operators. Okay, so this means that I erased the duality map. But plugging this in, if I instead keep this definition of J0B in terms of JF, and then also keep my map of parameters, which I erase, then these two are equal. Okay, so the 2-point functions aren't really test for duality, but they just determine the relative normalization of the operators.
Lambda B is the same, right?
Yeah, lambda B is the coupling in the bosonic description. Okay. So this makes sense because the fermionic guy is odd under parity and the bosonic guy is even. Okay, so that's.
How does that? Sorry, I didn't understand. Fermionic guy is odd.
Right. So psi bar psi.
Under there's a gamma.
Parity, it's in 3 dimensions.
It's odd.
It's odd under parity. And
because parity is one spatial. Okay.
Right. And this is even so for the duality to work, they have to be redefined. I mean, they have to be related by something which is also odd under parity.
Lambda 6 is odd.
It has K. No, lambda B. This is. This is
B, huh?
bosonic. This lambda is the bosonic
So that is
description.
I got you.
I have to keep the subscripts because to avoid. So that's all. Then once you have this, then this tells you that, for instance, if you were to calculate 3-point functions, then this should be and so on. Okay, so once you have the normalization, then you get predictions for all the other correlations.
Because if I put lambda B, JB as that, this coefficient should go over into the other one, right? And it does. I mean, one case you have lambda B over tan, lambda B.
Yeah, so it's
lambda F over tan. This
yeah. So let me actually write
some identities, I guess.
Lambda and 1 minus 1. So you're using tan and 1.
Alright.
So 1 minus 1. So the tangent turns into cotangent, and the rest. So that's and so this would be the prediction for 3-point functions. It turns out that if you actually calculate the 3-point functions, they're both 0, so it's sort of trivially satisfied. But we can then similarly calculate
The both 0, is there a reason?
I don't know if there any.
Or it just happens?
You might find a reason once you start the calculation, but I don't know if there's any deep reason. But the 4-point functions are not 0. So this is the prediction from the duality, and then we can try to calculate both sides and test the prediction. Okay, and of course, okay, so because it's the way. So anyway, this is the prediction from the duality. The duality, I mean, by Arani and Kurori and Jacobi, and they tested it pretty well for 3-point functions. So combined with, of course, Maldacen, it's clear that the duality holds for all 3-point functions, but it hadn't been tested for specifically for higher point functions. Although the thermal free energy probably takes contributions from them.
But how could they have tested anything if it vanished?
No, so although it vanishes for the 3 scalars, for other operators, you can like 2 vectors and a scalar. If I consider also other operators like this, for instance. So considering all the different 3-point functions, it was shown that it's true, but 4 and higher point functions are important also because in the Siliev theory, at the higher point functions, there are some ambiguities in the definition, which might raise some questions whether the duality actually holds it. And that's more for the 5 and 6-point functions, but the step was start with 4 to get to 6.
Also, given that Maldacen and Shiroman sort of almost completely fixed
3-point function, it's
the real test is at 4-point functions.
Yeah, and another thing is, of course, in principle for CFT, 4-point functions are determined by the operator algebra. So all the operator spectrum and all the 3-point functions. But if you work out the 4-point function in the operator expansion, it should get contributions from double trace operators. So it's sort of an independent test for that reason. Okay, so what we do in this paper is we try to test this at the 4-point functions, and that involves. But because 4-point functions are hard to calculate, what we do is we just calculate this guy as a function of lambda f for a particular class of external momenta. Okay, and then take the limit corresponding to the free bosonic theory and check if it agrees with the free critical bosonic theory.
And it would be harder to do the calculation of the bosons? Just because it's only cubic interactions.
It looks harder at least at first because
of the
quadric interactions. Now, I mean, it doesn't mean that it can't be done, but it is substantially harder at least at first. So we just.
But what you tested the.
Okay, so this is
free. What does that mean? But in some limit, you work in some limit.
Right. Okay, so we directly calculate this guy, and we take the limit lambda f goes to 1, okay, which corresponds to bosonic going to 0. Okay, and we get the finite answer on both sides, which agrees.
Okay. So just weak contractions. Yeah.
Yeah, so I mean, it's still critical bosonic theory. So there you do have to do a little bit. And then we also do the critical fermionic theory compared to the non-critical bosonic theory.
But just to ask what Shiraz was asking, just so I can understand, you can manage to do the calculation for all lambda f on the fermionic side, but not the bosonic side.
Well, no, I mean the bosonic side is just a matter of effort to do it. I mean there are I can't calculate the 4-point function actually for all values of external momenta on the fermionic side. and there's some more obstructions to that. But for a particular range of external momenta, we can calculate.
So one quick question. In these n equals 1 supersymmetric theories that we looked at a few months ago, the calculation was roughly as easy as doing it for the fermions, because in superspace it's only cubic interactions.
Right.
So perhaps in that theory you could do the calculation completely, and then you would have it exactly on both sides, since these n equals 1 theories are set.
Right. So now I'll roughly summarize how we calculate this. Yeah.
We compute 4.jj f0 and take lambda f to 1.
Right.
Match it with the free.
That means you have to match with the free critical theory. Free critical bosonic theory. Okay, so we have the expression for all lambda, and it turns out it's slightly complicated. But we just match it with the free.
Like in the do the free boson and then free fermion. Can you write down this psi with this fermion in terms of boson?
No, so the free theories aren't dual to each other. Yes.
So these are typically interacting theories. Is there a formula for psi in terms of phi? At arbitrary.
I have formulas relating the gauge invariant operators. I don't know if the scattering amplitudes give you a formula for the non-gauge invariant operators, but it's just a duality that relates gauge invariant operators to gauge invariant operators. I don't know if to write it in terms of the fields directly. So like there's not bosonization in that sense. There are ways you might try to. People have tried. You could try to do that.
There is bosonization for a gauge theory, right? We don't expect to be able to relate on physics.
Right. But I mean, it's not like you're writing the fermion as like the boson as an exponential or something. So maybe it's just a duality rather than bosonization, perhaps.
And maybe one other comment about this is it doesn't seem like particle versus solid term. Because at least in the scattering amplitude, the elementary boson maps to the elementary fermion. So it's a simpler duality in some sense.
Yeah, it's some anionic duality. Yeah, so just. So I'll just then quickly sketch how we do the calculations and then maybe I'll move on to open questions because either people already know how to do these very well or they may. Yeah. So to solve the theory, we work. The crucial idea is to work in light cone gauge. So in light cone gauge, the cubic vertex of the Chern-Simons term goes away, and you just have this guy. There's no ghosts either because it's just like a one derivative action. So we just have the Feynman rules are very simple. You just have your propagator, and you have gauge propagator, and we have travel vertex, and that's all we have. We can write them in double line notation as this. So then diagrammatically, if you have these things, there's just two things which you need to calculate if you want to solve the all planar diagrams. One thing is the exact propagator, which is, well, I just have to write down the expression for the exact propagator. This is this is just all the sort of rainbow corrections for propagator with multiple sort of suns setting or whatever. And then there's one more ingredient which you need is what you might think of as an exact off-shelf 4-point function for fermions, which is or what I call the exact ladder diagram, which is which satisfies this. So this is effectively allows you to calculate the exact off-shelf point. And this would be the exact. So in terms of just the ladder and this exact propagator, you can calculate any planar correlation function. So for example, if we want to calculate just a 2-point function, it will be something like this. So right, integral equation for this one was solved in our this actually Z wrote down the integral equation for this in the paper, but we no one solved it till Shaz's scattering and I actually solved this. We solved this actually quite a while before that, but we didn't know what to calculate with this. And then I thought, after I saw this, just 4-point functions was the only thing I could think of to calculate this. But okay, so the main thing in green is this integral equation, and so I'm drawing the momentum like this. So you can think of it as P momentum flowing in here and Q flowing back out, and Q flowing here. And here it's like R flowing out and R plus Q. So this ladder operator is a function of the external momentum, and in particular it's a function of this momentum Q. So it turns out, in general, it's hard to solve this integral equation in general unless you restrict yourself to Q3, only Q3 being non-zero.
So that's 4-point function of elementary equation.
This is the 4-point function of the elementary non.
Then you get more to get to that.
Okay, but using this, you can calculate the 4-point function of the cage invariant operators, which will look like, which will involve diagrams like this. Yeah. Okay. So this is really just a term in the effective action, a 4-point interaction vertex in the effective action, not so much a 4-point function.
Maybe you come to that, but when you go from here to there, is it just planarity? You only have to include the ladders between adjacent edges, or
no? You include any ladder as long as the things don't intersect.
It can be between. I mean, you could have one ladder going like that and another going around. And so on, right? There are multiple ladders.
So one way of doing it is first, we can define like an exact vertex, which I would define as just B vertex plus a ladder.
Okay.
So then you have, this is the exact vertex. So then you have a term with just exact vertices, which includes all of these type of ladders. Then you can also have a term
with a ladder between.
like this, like a cross.
Exactly.
And then the rest is like a permutation of this. Yeah, so these are basically the two classes.
But by sewing together basic ladders, you build up.
Right. Well, this is, you're saying,
Yeah, that's true. But just one example, but then you could also have one ladder going like that and another between two other adjacent edges. Isn't that also possible?
so this exact vertex means that you have ladders like this.
That you do. But can't you have, just as that ladder between these two, can't you have a ladder which goes between
Okay, so
these
this
in simultaneously? Or
this
is that
will be non-linear.
That's not linear. That's what I wanted to ask.
In a like maybe if we had a higher point
I mean, I
function.
could draw that other ladder around.
If you do a 6-point function, I mean, then you get stuff like this.
Okay,
But for 4-point, I think
this is also non-plane.
this one will be.
I could draw them so they don't overlap by going around.
That's not good.
Yes, because with the arrows, it won't work. Right?
The arrows it won't work.
It won't. Of course, here planarity isn't the right word to use because there are diagrams which are planar but circular also because it's a vector one. It's not a matrix.
Maybe that's the point.
But here, I think even those would not contribute. I'm not.
Even in a matrix theory, those going around would be counted as subplanar. Yeah, I mean, you're supposed to put all the stuff in one end of a fundamental line. That one is subplanar.
But it comes because of the arrows, basically.
Yeah, the statement of a drawing on a plane is a bit.
You know, I mean, because
For free energy, it's correct. But maybe with the external lines.
so if you have something like this, if going around would
I see.
be like.
Yeah. Right,
Okay.
So, but you know what? Even for the 6-point functions, you could probably just get it all by gluing ladders.
What do you mean gluing ladders?
Meaning taking, once you know the answer to this particular 4-point function, by putting many of those things together and making integrations.
Right, they're all. You just need the ladder and this. That's all you need. I mean, this is just to convenience you to find exact.
I agree. But I'm saying for arbitrarily high point.
Yes, so arbitrary function, all you need are these two and
then you get it.
but the gluing together is sort of the vertex I see you do once and for all. But the other one, you do diagram by diagram, right? You choose some pair, you put the ladder between. I don't know how it works.
Yeah, so for any function, you have to draw a finite number of diagrams. Right? It is that you don't have to do any more infinite stuff. That's all. But yeah, you will need more and more diagrams for higher point functions.
But maybe you could come up with a formal proof. And let's say for the n equals 1 supersymmetric way, maybe you have to come up with a formal proof that they're all equal, even if it's actually hard to calculate.
Yeah.
You mean there's a formal proof for the ladder being equal to?
No, I don't think the ladders themselves will be.
Right.
But since you can get, you've got an explicit integral equation of the ladder, and then you can build arbitrarily high correlators by gluing these ladders. So you've got some integral, some expression in terms of this object which obeys an integral, which obeys some equation, which you know.
Right.
And then maybe actually doing those integrals is tough, but you could prove that.
I see.
Yeah.
The answer is.
And the ladder depends on lambda.
Right.
In a non-trivial.
Right.
At least in a way it looks non-trivial at first.
But maybe you could shoot then for an all orders proof for a class of correlators, a class of dynamics.
Right. Okay, Okay, so to do this you have to solve the integral equation. In principle, this guy has 16 components because it's like 4 fermionic fields which are 2 components. So it looks slightly challenging, but you can rewrite it in a way that there's really only 4 components that are non-zero, which really split into 2 sets of 2 that create a couple of differential equations. Okay, so I can just sketch how that works.
Whether the spin is oriented upon momentum. Okay, you didn't. I'm just asking. Your split must be something like that, no?
Well, it's more that, okay. This was easy because we had we use H3, that function where So I mean, it turns out you can rewrite this in terms of. I don't know if people would be interested in the details of that, but it looks like 16 components. But if you sort of think if you the way we imagine it is you imagine you're not going to calculate the data diagram, but you're calculating a series of rainbow corrections of f, where f is some arbitrary matrix. Then at each stage, only when you work out the gamma matrix algebra, only the plus and 3 components contribute just by. It's just a coincidence of the light cone coordinates. So it turns out that in light cone region with light cone coordinates, the 16 components, most of them are 0. So there's effectively just 2 couplet sets of equations. But still solving these 2 couplet sets of equations is difficult. So as 16 equations. 16 components. But to solve this, the resulting differential equation for an arbitrary q turns out to be difficult, and then we only can solve it for q where 1 component is non-zero. And technically that's if you remember these problems, we can only solve this for.
So in the gauge where A minus is 0,
Yeah.
you can solve it.
Correct. So A minus, right? And so for 3-point functions, though, that combined with the fact that 3-point functions give you a unique form is enough to determine the complete 3-point function. For 4-point functions, it doesn't actually determine the 4-point function, but it's still enough to test the duality. Okay, because.
But 4-point.
Yeah, so 4-point functions, we can't say we calculated it in the most general form class of momenta.
I mean, rotational invariant. The end result is gauge invariant, rotational invariant, and so on. And
But
it doesn't fix everything if you know it in this.
Right, that doesn't appear to fix everything. It might fix everything if you're very. I don't think it can fix everything. I mean, I haven't.
But let's say, so 4-point functions are functions of one cross ratio is one cross ratio. And you're going to compute a cross ratio is one dimensionless real number.
Right.
And you're going to find one function of a real number.
Well, okay. There's 2 things we do. One is, of course, we'll calculate this ladder diagram for Q3 not 0.
Yes.
Which means that I can calculate the function. I can, in principle, evaluate the integrals where this. Where these only have 3 components in the 3.
Yeah.
Okay. Now I don't actually even do that. I'll just keep some of these the same. But we do have an unevaluated integral for these.
But just let me understand, I'm finding it hard to translate that. So would you in the end be able to get a correlation function as a function of one number, one variable?
Yeah, it looks like you'd be able to get.
So that sounds like it might have all the information.
That's what roughly I was thinking, but I wouldn't make that precise.
But it might be quite exciting if you could, because apart from duality, just to have an exact expression for the 4-point function. And then you look at it and operate.
Even in
sounds interesting, right?
I mean, why isn't it what Shiraz was saying? There's only one cross ratio, that's clear.
Right.
So it's some function of that cross ratio. And as you vary Q3, or you in fact have 4 independent, let's say, or if you keep some the same 2 independent parameters, don't you sweep out the entire cross ratio space? I guess we have to go to position space. I mean, at least I usually think of cross ratios there.
Right, so of course, all the work, when you think about it, firmly is in position space.
Right.
I couldn't find
Sandeep
forms on the, what the analog of a cross ratio is in momentum space.
I know. But just roughly speaking, though, if you have one function and you've got one function, you expect more or less to have the same.
Right, but since they're all like in the same direction, it's like a planar.
Maybe.
I can't use conformal transformations to map this to an arbitrary set of momentum. So can you use this? Forget about that thing. I couldn't think. I didn't think I could do that. So. Okay, so anyway, the point is we calculated in this thing, and
is it here you can't use conformal transformations?
Well, I convinced myself we can't use them, but I didn't really. I convinced myself enough to not pursue that further. But it might. If you have 4 points in a thing, can you? Like 3 points, I can take them to a line, but the 4th point, I don't think.
And you want to be careful of the fact that these are not points, but these are momenta.
But I think it is worth thinking about that a bit more.
Yeah.
But
I mean, the way you get one cross ratio in position spaces, quantum ways, you take 1 point to 0, 1 to infinity, 1 along the x-axis at 1 unit of distance, and then all remains is the dot product of that with the second point from rotational invariances. I mean, roughly that's what you would say.
So maybe at least you're right. Right? Actually, maybe perhaps you can uniquely. At least you can argue that it covers. Yeah, I just left it at this. So perhaps one can see that.
Right. Because I say, if you can, apart from these theories are interesting. Apart from the fact that they have duality, they have interesting physics.
Right.
So if you have a 4-point function exactly, that's quite rare in quantum field theories. That
Right.
But interesting to study by itself.
Right.
Yeah, okay.
So anyway, so I guess I'll speed up. So once you calculate this, we just check the duality as I said, and
give us a sense of how complicated they are.
So suppose we sorry, I never really answered this. Well, the answer is relatively. Sorry. Right, so it involves like Dayalbagh functions of lambda, and so it's.
Until you do the final, yeah.
Right.
So the answer has some dramatic simplification as lambda goes to 1. It's complicated answer.
Right, it's complicated and it simplifies when lambda goes to 1. It doesn't. Even then, it doesn't imply that. Then it simplifies and it's just cotangents and tangents. But in the intermediate part, at least, as far as I could see with Mathematica, It was just the best you could do is you write it in terms of various special functions came out as into like Dayalbagh. And this is if you suppose you fix all these momenta, so you just have one momentum scale.
Yes.
Okay. Then it's just a function of lambda times momentum. So that function of lambda is fairly complicated. I mean, when you plot it, it's relatively simple in that it just goes up like this. So if you scale all these to be
Pretty confusing. There one. There should be one cross ratio, but now that I count it.
yeah.
You can take one point to 0, another to infinity, 1 to
1.
But then the coordinates of the last point are can be brought into a plane, but then it has two values, so it seems to be two. Yeah, exactly.
Right.
Right. Sorry. Okay, go ahead.
Right.
What was
But
the
anyway,
what was this?
So this is. I can write this here. We can keep. Yeah, we can write this whole thing so that it's like the same momentum coming in one vertex and going out the other. So it all just depends on one momentum. Then all the momentum dependence is fixed by conformal variance. And it takes on the form whatever the power is. The 4-point function is is some function of that times momentum, and it's just an increasing function of that increases fairly fast. I mean, right? I have the explicit expression.
It's very complicated.
It's very complicated, but when you take the limit lambda goes to 1, it simplifies enough that you can just
And so, yeah. So it scales by dimension analysis as p to some power, but then there's some complicated function of this ratio. Of lambda and also of this ratio of p3 over.
Well, I can't.
You have at least two independent.
Well, I can't write it in closed form when I keep that ratio. So for a particular choice of that ratio, it's just it's a complicated function. Okay, and then you can see how that as it approaches 1, we put it into the formula and check the duality.
But in terms of an integral, you have it for all.
Right, in terms of integral, we have it for all. But the integral is so in terms of unevaluated integral, you have, of course, have it for all.
The bosonic part of the calculation will have more complicated diagrams coming from the Seeger diagram.
Right. So we do the calculation just in the fermionic theory, in the interacting fermionic theory, and then we can also consider the critical fermionic theory by building up stuff. And we'll compare this to the free bosonic theory in the limit lambda f goes to 1. So we don't. So bosonic theory, there's more complicated diagrams, and we didn't calculate it for the intermediate range. It's consistent with the duality, but it doesn't.
So just going back to so in the n equals 1 supersymmetric theory, for example, you once again have to get an integral expression for all momenta. And there, once again, I would imagine that the integrals would be hard to do. But already first one could try there, just to show that even if you can't do the integrals, that it's the same on the side.
Yeah, the unevaluated integrals.
Yeah. That sounds interesting. Because the fact that it's so complicated makes it a very significant test.
mean, in some sense,
For at least J0, 2-point and 3-point function did seem to be too hard to do, probably, but 4-point functions.
But the 4-point function, I think, significantly more.
More integrals.
More integrals from the technical point of view and from the physical point of view has much more information.
Maybe.
so I mean, I'm just going to quickly. So how much time do we
You remember last time, right?
rest?
By the way, what's the story about the theories with number of flavors?
Right. So that's some other thing which I can. I'll just. So of course, why did we study these things in the beginning? Like to begin with. So the idea was that you have these this tower of operators, the higher spin operators, and what happens in super Yang-Mills or ABGM is you start out with the infinite tower of higher spin operators. As you turn on interactions, all of them, all of these develop very large amount of interactions. So the bulk dual theory, when lambda 0 might have higher spin fields, but at lambda goes to infinity, we would want only we expect only a few operators to have a small enormous dimension, hence only a few massless gauge fields in the bulk. Right? And clearly for bifundamental style theories, it's still possible that happens. Okay, so for example, UN cross UN Chern-Simons coupled to bifundamental fermions could be like Einstein, Maxwell, with perhaps axion and dilaton because of the Hooft coupling. Because you can slowly vary the Hooft coupling, so you might also get axion and dilaton.
No, it's not really an operator. Very true. It's not clear.
Well,
I use in string theory.
Right. So you can change lambda in a way that will give you a dilaton, or you can change lambda in a way that violates parity, and I'm guessing that's true to an axiom.
Yeah, right.
Okay. So it's. I mean, let me just. So if you change k, okay, so if I write this as. So in general, we could consider the theory like this. Then. Okay, and why it's interesting if you study the Hooft limit, it could be to the Einstein Maxwell with John. If your goal then you want to just consider that you could study the theory with k fixed and large n, just because ABJM can be studied with k fixed and large n in principle, then that would not have a dilaton. And could be as simple as Einstein-Maxwell gravity without anything else. A small negative cosmological constant. If you don't want a Maxwell field, then if you remember the ON theory does not have charge current. So if you want to say ON theory when k is 1, it could be pure Einstein gravity with a small negative cosmological constant. Okay, so that is like that. Yeah. So if you can say this at k equals 1 and large, then this could be. I mean, if there's a field theory dual to pure Einstein gravity with small negative cosmological constant, this is only one I could think. I can think of it might not. But I can think of, I mean, yeah, it's only on that. So that's why these. If we decide in the Hooft limit, you get lambda, and presumably you can continuously deform lambda effectively. So that should map it to some sort of marginal operator.
But first, just in the large Hooft limit itself,
Just
you might want to look at that.
Yeah, you might want to
That's
look.
what you want to do first, right?
Right. I mean, even that, I don't think we can say much.
Yeah.
Right, but it's worth. I was just distance. Right? So then the question is, okay, we can't do that, but in what regimes can we study this? Okay, so we can keep, one of, so we can vary all these different limits, these different values. So if we take n1 larger than n2 and k2 to infinity, that's effectively the vector model. Okay, but we could instead consider a different regime where we take, say, n1 large, k1 to infinity, and k2 smaller, and then that's like Chern-Simons coupled to a large number of flavors. Okay, and then there are other limits. Okay, so we can ask, I mean, in what limits can there be dualities? And in what limits would the enormous dimensions be protected? Unprotected. So
I was actually first asking about what might be a simpler limit in the general case, which is k2 0. So you don't gauge the second group at all. You just have the analog of cyber duality. We have one gauge group and some number of flavors. So
right.
And then how does this is probably known, but how does the map go?
I don't know if it's known actually, but if you take k2 to infinity to make it 0, k2 to infinity, then you can ask the question, is n2 less than n1 or much bigger than n1? If it's less than n1, then it's just sort of like asking, does the duality extend to 1 over n? So if we knew, if you believe the duality works for finite n and k, you can guess the extension.
But the map of operators is pretty clear just from symmetries. Psi bar psi with indices maps to 5 and 5, 5.
Probably, because there's a global set.
Right. So that would work case where n2 is less than n1. If n2 is bigger than n1,
I mean, in cyber
I'm not sure.
There are some interesting twists even there. Right?
Ah,
It's not such a
deletions.
obvious map. Mesons appear as explicit.
So what happens to Gibeon-Kutta subduality? So in the supersymmetric case, this is Gibeon-Kutta subduality. So does Gibeon-Kutta subduality has some restriction on the size of n2?
It does.
Gibeon-Kutta is more or less cyber.
Is cyber in 3 dimensions, which is?
But does it have a similar story like the mesons of one theory appear as the explicit guidance of fields in the other description? So you get more fields which are singlets.
Yeah. Actually, if you just take this Gibeon-Kutta subduality with the simplest case, it was not actually worked out by Gibeon-Kutta, Benini and calculators, where you take the chiral multiplets purely to be fundamental. Not like Cyber, where they're fundamental and anti-fundamental. You see, in 4 dimensions, you need that for having non-anomalous theory.
Then you can't get the meson.
Then you don't get the meson. So it's actually a very, very simple story. It's a self-duality. You don't have to. On the other side, you don't need to deform superpotential and so on. So it's an even simpler story. So, but what happens? Is there some bounded NF in Gibeon-Kutta subduality?
This is like you're saying in AVJ duality.
Yeah, for instance, right. Yeah. That is right. Some.
Well, in AVJ duality, they're both equal Ks.
The Ks are equal, but
what I'm saying that if I just consider the very large flavor limits, then interactions are effectively very weak.
I understand, but in AVJ duality there is some bound, right? So the n minus m.
No, that's just related to the K being bigger than n.
K being bigger than n. Right? But could you write that up? What was it? N minus m is K is greater than n minus m. Is that right?
It's like if you write it like this.
Yeah. That K is greater than n. What do we ask?
K has to be greater than n, because in the other case we'll subtract K away in the dual. Remember what?
NF is it left in just ordinary Gibeon-Kutta subduality. NF is left invariant. This is like cyber, right? NF is left invariant. And and the number of colors changes, and the number of colors, NC has NC goes to K minus NC, and then a plus NF or something like that, right? I can't remember that one.
Maybe in Seiberg duality, NC goes to NF minus NC. In 3 plus 1D, Seiberg duality.
Sorry, what I was trying to get at is there a bound on NF? Does NF for the duality to hold have to be less than a certain amount? You're saying no?
I'm saying no, I mean, there's just a bound on K.
Yeah.
But it's not great NF. In this case, both are gauge.
I understand.
If you don't gauge one, I don't know what the duality is.
So that's Gideon's view of something. Gideon's view of talk about fundamental flavors.
So in that case, I expect there should be a bound that the flavors should not be bigger than N.
Maybe there is. I should.
At least, but certainly for the non-supersymmetric case, I don't think it will work if flavors is bigger than N.
Mm-hmm.
Because you have a very large number of flavors, and it's just like free bosons or free fermions. And free bosons are not dual to critical bosons or critical fermions. Also, the number of flavors affects the shift of 1/2 in the fermionic field. So I don't think. So I think once the number of flavors exceeds the gauge group, or maybe the gauge group by 2, it's not going to be possible for there to be the duality. According to, but supersymmetrically there may or may not be.
So bottom line is, if I just took one gauge with U and C, Chern-Simons, and added NF fundamental fermions, all in the fundamental representation, then the bosonic dual is probably NF bosons.
Right, so that might work for NF less than N.
And I guess the critical coupling now with flavors, maybe you can take 5 to the 4 in a few different ways or something. But there's one way or something. Or maybe only one way is there.
I think if you want to maintain that UN symmetry,
Then only one
then
way.
there's probably
Take 2 5s, 2 5 daggers, you pair each one up. That's it.
Right.
Nothing else.
Right.
Okay. You can't take the 2 5s, make them into a symmetric, and the 2 5 daggers into symmetrics, and then
Maybe that's
all that
true.
kind of stuff.
Yeah, it's like how many ways are there of coupling two fundamentals with two antifundamentals?
Yeah.
And there are two.
Yeah, that's what I was thinking. We take,
Yeah. Because you can couple symmetric and antisymmetric and then fuse.
Yeah.
So maybe that outcome. There's a little more to it. Yeah. Of course, the supersymmetry probably picks up just one. So, in the supersymmetric case, it's very tight and well understood story. And the non-supersymmetric case, it's very interesting.
No, but you're right. Probably doing the supersymmetric case just probably.
Yes.
Oh, so you could try calculation to test if you just have a small number of flavors. In principle, that calculation would be doable, but it would require knowing this ladder diagram with Q plus minus also constant.
So I didn't understand that.
So suppose you want to test the duality for a small number of flavors.
In a way, that's not just n times. You want to get the first one over n direction.
Right, you want to get the first one. So in that case, what's the simplest quantity to calculate? So because now anomalous dimensions aren't protected,
Yes.
the easiest thing to calculate would be just the anomalous dimension of the scalar.
Yes.
That's the easiest thing to calculate. So that's just the coefficient of the logarithmic divergence in this exact vertex of the scalar.
Yes.
So you can ask what sort of diagrams you would need, and you will need diagrams maybe like this,
Right.
okay, which means this is the ladder, or
I understand. Right.
to
Just sew it up.
You
You
have
need
to sew up the
yeah.
ladder in
So you need all the momentum.
Right, so you need all the momenta, and that's the original reason I was looking at the ladder.
Yes,
I want
yes.
I couldn't solve it for Q plus minus not zero.
Sorry, you're thinking of the case again with two gauge loops, one of which is much smaller.
Or even your case of flavors.
Even there, the anomalous dimensions will get lifted.
If you want, or just even a single flavor and 1 over n corrections. The three are very similar questions.
I see. I thought I have flavors. What maybe I was thinking. Even though you're still doing planar diagrams, you still lift the anomalous dimension.
Yeah, I mean, if you've got the number of flavors comparable to the number of colors, that's about as hard as something.
That's as good as bifundamental with the gauge, the other gauge group activity. So that can also have holographic tool. And to try to check the duality at leading order in you in principle, of course, there's just a finite number of diagrams to validate, but the integral equation for the ladder has to be solved.
As you say, that's just the 4-point function at one momenta. You know that, you know it a lot.
Right.
Shiroman, related to this, the anomalous dimension of the scalar is a tough one, but the anomalous dimension of all the others should be just computable from Maldacena Shiroman and using what we did in our first group, following the logic of, do you know what I mean? Completing this.
I know the logic in the first paper, but that just sort of gave you from the.
We got the first lambda square correction.
But related to given the divergence of J4.
No, what I meant was that, you could, the part of the paper where we took K with P.
Right.
That part. And then we were able to compute the first anomalous dimension at order lambda square.
Right.
Of all the Heisman grounds.
In principle,
yes. This was before Maldacena Shiroman.
Right.
So now with Maldacena Shiroman, we could presumably compute the first anomalous dimension of all the Heisman currents at all the values of lambda. This will not really test duality very much.
It's nice to.
But I think it would be nice to have an explicit formula. Somehow.
I'm not 100% sure that I understand. So Maldacena gives, but it doesn't work for the scalar, you're saying.
But it doesn't work for a scalar because the scalar is not, it doesn't have a null state condition. All the other operators have del dot j is equal to something smaller.
Right.
But for the scalar, we don't have that kind of equation.
Indirectly, you got some equation.
Right, but this is very, very, very direct. You see, because del dot j is almost 0. Had del dot j been equal to 0, we would have had delta is equal to 1 plus s.
Right.
So since we know del dot j is non-zero, but we know what it is, we should be able to compute the first correction to delta is equal to s plus 1.
Right.
Using that equation. And we can talk about it.
Right.
I don't think anyone's done this. And in this bootstrap business, there's another interest in this question. How do these anomalous dimensions go as a function of x? I don't think this would be hard calculation. I think it's worth doing.
Right.
Maybe we can discuss.
What is this? Sorry, I was trying to figure out why the anomalous dimension get lifted or not. I got confused. What are we talking about? Sorry.
Something we've discussed before. She came up during the strings meeting. As Shiroman says, nobody's done any 1 over n computations in this whole business. Right? All calculations have been leading order n, and then there's some indirect arguments that things might extend to 1 over n. So, now one calculation you could try for is anomalous dimension of operators. Now, Shiroman was talking about the scalar, which I think in some sense would be the hardest. Because everything else, you see, all the other dimensions, like if you remember in our paper, the argument that the scalar was not renormalized was the most difficult.
What is the scale? Side by side.
Was the most difficult of the arguments. Right? The rest followed immediately from representation theory. And then we had to do some 3-point function word identity kind of stuff for the scalar. So for the rest, there is a simple argument that a leading order large n, you've got something not renormalized. That argument relies on the fact that the operator obeys the equation del dot j is equal to 0. Now the operator does not really obey del dot j equal to 0. It obeys del dot j is equal to something. But Maldacena and Shiroman tell us exactly what that something is.
So they tell exactly.
So actually, what is it of it? Del dot J equal to
J times J, 1 over n times J times J plus 1 over n squared times J J. Okay? And the 1 over n and the 1 over n squared have some functions of lambda which I believe Malvisen and Shiroman are completely independent. Okay? Yeah. So now using them, we know exactly what the quantum corrected del dot J equation is. Since we could argue on representation theory grounds that if del dot J is equal to 0, delta was equal to J plus 1, I think we should be able to argue, I think we should be able to use that exact answer to say that given that we know that del dot J is not 0, but we know what it is.
Right, if you know what it is exactly, then it's fine.
Yeah.
Yeah, del dot J. I was not sure whether they actually determined del dot J for them or just in principle.
Shiraz, then it will.
So that was
Okay, I will have to check.
But then presumably the enormous dimension will get extracted out of a 2-point function. And then this argument, if it introduces J square and J cube, then you need information about higher point coefficients.
But the great thing is only at leading large n.
In leading large.
So the only parts that contribute are the 4-point functions when 4-point functions when they completely factorize. So they factorize into products of 2-point functions, which you know. Yeah. Because they're explicit 1 over n separations. So to get to the same order in n, you need to take compensating factors of n. So you need to have that in. So I think, this in the end is the reason that Malvisen and Shiroman were able to solve this theory. Right, so I think that in this limit, okay, now Shiroman's telling me they don't have an explicit formula.
They might have it, but
I never thought that people that cared in results, but okay, I should do it. I thought that they had computed everything, including this. I think it's straight. I have the feeling, unless as Shiroman said that formula is not there. If del dot J is known, I think it should be straight. And I think it will carry a lot of information. Because this kind of thing is upgraded,
right.
In current interest to these bootstrap people, right? And they do all kinds of stuff. Here we just do a calculation.
Right. So then, okay, one more thing, just to
that seemed to me like fundamental.
What should do the boson problem?
No, it's just the Chern-Simons action as a sign.
if you have 2 Chern-Simons,
Even if you have 2, it takes it away from being e to the power I theta to cosine theta. You can combine configurations to make it real. But cosine doesn't have the property that it's positive. Lattice gauge theory people have great trouble simulating actions unless you can write them as e to the power minus beta times a positive vector. This is called the sign problem.
Right.
And but I try to think about this because I also agree it's very. The thing that I kept hitting against, and maybe I just followed it through badly, was that whatever else you do, you keep getting the sign wrong. I may not follow.
maybe I'm also not that. I mean, that is perhaps, but 2 Chern-Simons would be easier than.
No, I agree with you. In that case, you can combine configurations. You can take a configuration and a parity transform configuration. So it gets rid of that e to the power I something. But I think it becomes cosine. I mean, please do think it through and tell me to. Yeah.
I guess cosine you can add something, just because it's still bounded then.
It's bounded, but it becomes negative. I don't know if lattice gauge theory people know how to simply understand. I mean, the integrand doesn't stay positive. That's their sign. Maybe something goes wrong.
Yeah, you're right. The integrand doesn't say that.
And that is what I believe. That's what, when I talk to the lattice gauge people, that's what they tell me. They don't know how to deal with that.
Right.
Because Monte Carlo doesn't work for that.
So they can't do anything in QCD with theta.
I suppose.
Because nature spares them from it. Is there aside from this, is there a discrete, I'm just curious, is there a discrete version of ALJ? The standard plaquette action is gives you an F square. Maybe you just flow at low enough and large enough distance to the. If you can somehow bring about parity violation, you just flow to ALJ. Is it? It was something I couldn't quite construct it clearly.
You're saying just to take a massive Fermi axis.
Yeah, you could do that. If you could do the latticization, and then happens also you will have some doubling inside and but it seemed like an indirect switch.
But somehow I think this you can get around. I have to think this is something.
That's why I'm asking the
Yeah.
easier question. I think this is I didn't spend enough time.
Yeah.
I couldn't quite come up with a nice mechanism. I'm sure.
At least if you're willing to be a bit baroque, I think you'll be able to get around this. But actually do the calculation somehow, the thing that my understanding is people just don't know what to do with integrals that. Yeah.
I guess maybe.
Any questions from ICTS?
Offline.
Okay. Any questions, anyone? I mean, we have plenty of questions.
The duality that when you check for the co-point function, you could not check it for any lambda. I mean,
Yeah, it is just.
is this some technical?
No. To do that, you have to calculate it for in the bosonic field,
which you
outside of the field.
each time.
I mean, which involves like Seagull diagrams and all this. That just seemed not feasible.
But this is the thing that would be easier and N equals 1 theory.
Right.
Because the N equals 1 theory is about as hard as the Fermi.
Yeah.
Because it's only Q.
Yeah.
So, this I think one could do.
Yeah.
I mean, maybe also do.
If you do it in superspace using
It's about as hard as the Fermi. Right?
Yeah.
Roughly.